Some of the Big Bang Theory's validity is being questioned in light of new data found by the James Webb Space Telescope. We recently created a surprising discovery with this telescope that is transforming the world of physics. The most recent photograph taken by this telescope has produced persuasive arguments that have caught experts off guard, putting an end to a lot of rumors. The most recent find made by the telescope is visually stunning and capable of changing our comprehension of the universe. Discussions among experts, which this image has resolved, focus on the perception of the cosmos. The stunning image taken by the James Webb Space Telescope challenges our comprehension of the universe. This finding provides an answer to one of the primary issues in astrophysics, the age of the universe and its rate of expansion. Researchers from various fields have been baffled by this unresolved problem and have carried out numerous studies in search of answers. Cosmologists investigate how the universe originated, how it works, how it has evolved over time, and how it might end. Significant advances have been made in this field over the past century. The most widely accepted theory, the Big Bang cosmological theory, holds that the universe has been expanding for roughly 13.8 billion years, beginning with a dense and extremely hot state. The Hubble constant indicates the speed at which the universe is expanding and is used to measure this growth, but figuring out how to measure the Hubble constant is not straightforward. There are two primary methods: local measurements and measurements of the early universe. Objects in space, like stars and Typeus supernovae, which are utilized as standard candles because of their consistent brightness, allow astronomers to measure how far away they are and, as a result, compute the Hubble constant. Throughout the universe, at varying speeds over time, scientists can determine the Hubble constant. The first approach involves measuring the early universe. Scientists use readings of the cosmic microwave background CMB radiation discovered in the 1960s as the afterglow of the Big Bang. This generation of microwave energy occurred when the universe was only 380,000 years old. By taking note of the minute ripples in temperature and polarization released by the CMB, astronomers can determine the age of the universe and its expansion rate. However, these methods don't always produce consistent results. Local measurements indicate that the universe is expanding at a rate faster than CMB data suggests. Scientists have been working hard to understand why the results differ and to unravel more mysteries of the universe. Further studies are underway, as the measurement differences indicate that we do not yet understand all the signals or that there are errors in one of these approaches. Thanks to the James Webb Space Telescope, we can peer farther into the darkness of space than ever before, revealing components of galaxies and planets we never imagined possible. Scientists hoped the data would aid them in determining the Hubble constant, but the first wave of data has revealed unexpected results that don't align with expectations already in place. Could this information give us new insight into space? We may need to rethink what we understand about the workings of the universe. We might discover particles and forces previously unknown, or we may find that dark energy, the mysterious force speeding up the growth of the universe, needs to be rethought. With each new discovery, our ideas about space evolve. For example, the cosmic microwave background radiation, discovered in 1965, provided persuasive support for the Big Bang theory. Prior to that, scientists believed the universe would last forever, expanding at a rate that remained constant indefinitely. Evidence showed this was not the case in the late 1990s when it was discovered that the universe was accelerating in its expansion. Scientists also learned about the effects of dark energy. Every time we learn something new, we test whether it fits with previous knowledge and develop new ways of understanding the universe. Without this process, the challenges we face in cosmology could not lead us to better insights. Although this problem is complex, it is also exciting because it drives us to develop better tools to explore space. Scientists around the world are interested in this cosmological puzzle because everyone wants to know more about the universe. Primarily, it demonstrates how science is always changing as we learn more about the structure and age of space. The concept of structure and age tension goes hand in hand with Hubble tension and refers to how matter is spread out in space. Scientists use this information to model the structure of the universe and observe how it has changed over time. Some areas of space have many galaxies clustered together, while others are relatively empty. Scientists employ various approaches to determine how much this dispersion affects the universe. One possible way is to examine how distinct densities of matter, such as galaxy clusters, bends light from distant galaxies. This phenomenon, known as gravitational lensing, allows us to see the effects of dark matter, which does not emit light and is therefore undetectable. Scientists also analyze the cosmic microwave background CMB radiation, the afterglow from the Big Bang. This light has been traveling for about 13.8 billion years, carrying information from the beginning of the universe. By studying the CMB, scientists can understand how the universe was full of irregularities when it formed. However, this data does not match the large-scale irregularities observed in the current universe. The non-spherical distribution of gravity suggests that matter in the early universe was more uniform than it is now, as observed through gravitational lensing. This suggests that something fundamental is missing in our interpretation, bringing us back to the mystery of dark matter and how it operates. According to researchers, the James Webb Space Telescope has enabled scientists to redefine their work, thanks to its unprecedented ability to reveal new insights into the universe. The James Webb Space Telescope and the desire to examine whether a potential error in the Hubble Space Telescope's measurements could be causing a discrepancy have revealed the same deviations, which is worrying. Somewhere in the middle of these two findings, our comprehension of the universe must have a fundamental flaw. Rice stated in a conversation with an astronomer magazine in the United States, using the new space telescope has allowed us to take a deeper look at the universe by its sharp infrared view and study cosmic distances with ever more precision. Both dark energy and dark matter are mysterious parts that make up a sizable portion of the universe. Despite being elusive, their nature remains a puzzle. Black holes have been the primary cause for particular gravitational effects. There is increasing interest in figuring out how dark matter and dark energy might influence these cosmic phenomena. Please share your thoughts in the box provided. If you enjoy the video, please like and subscribe, and many thanks for watching. I hope to see you again in the next one. As scientists, you keep looking at the James Webb Space Telescope's data. The fundamentals of contemporary cosmology are facing unprecedented scrutiny. The telescope's ability to observe distant galaxies from just a few 100 million years after the Big Bang has challenged existing models of galaxy formation. Contrary to previous beliefs, the initial universe appears to have hosted more massive galaxies than expected. Based on these findings, either galaxy formation happened much more quickly than we previously thought, or a fundamental modification of our comprehension of the underlying physics is required for the early universe. One new theory to provide an explanation for these discrepancies involves changes made to the lambda-CDM model, the current standard model of cosmology, which includes cold dark matter CDM and a cosmological constant lambda representing dark energy. Some physicists propose that dark energy may not be constant at all, but instead may change or interact with dark matter over time in unknown ways. This dynamic form of dark energy, sometimes called quintessence, may account for varying rates of cosmic expansion observed at different epochs. Other researchers are exploring alternative models of gravity, such as modified Newtonian dynamics MONT or scalar tensor theories, which propose changes to Einstein's general theory of relativity. These hypotheses attempt to explain phenomena like gravitational lensing and the formation of cosmic structure without invoking entities such as dark matter or dark energy. While controversial and not yet widely accepted, these ideas emphasize the increasing willingness to call into question long-held assumptions in light of new observational data. The James Webb Space Telescope has also opened up opportunities to examine the atmospheres and chemical makeup of exoplanets, some of which orbit in their stars' habitable regions. These studies may not have a direct effect on our comprehension of cosmic expansion, but they add valuable context about the evolution of matter, star systems, and the potential for life in the universe. The chemical fingerprints the JWST detects in these environments may provide clues regarding the wider spread of elements in the universe. Another important piece of the cosmological puzzle is the nature and behavior of inflation, an extremely rapid expansion of the universe thought to have occurred just a few milliseconds after the Big Bang. The inflationary model contributes to explaining why the universe appears so uniform on large scales despite the vast distances between regions. However, the precise mechanism behind inflation is unknown. Various speculative models exist, including those involving scalar fields and quantum fluctuations, but no single theory has yet been confirmed by observational evidence. The most recent data from the James Webb Space Telescope may also provide fresh perspectives on the inflationary epoch by studying the distribution and structures of the earliest galaxies. Researchers hope to uncover patterns that either support specific inflation models or refute them. In the event that anomalies, such as irregularities or unexpected clustering in the cosmic background, are found, this could point to physics beyond the standard model. In parallel, theoretical physicists are working on unifying quantum mechanics with general relativity, which remains one of the greatest challenges in modern science. A successful theory of quantum gravity could fundamentally alter our comprehension of the universe's origins, including the Big Bang itself. String theory and loop quantum gravity are two major approaches, but both remain highly speculative due to a lack of direct experimental support. All of these efforts, whether observational or theoretical, point to a single, unified truth: our comprehension of the universe is still developing. The James Webb Space Telescope has not only deepened the mystery, but also given us the tools to ask better questions. As more data becomes accessible, particularly from long-duration missions and complementary instruments like the Euclid Space Telescope or ground-based observatories like the Vera Rubin Observatory, we may soon find ourselves on the verge of a new paradigm in cosmology. Until then, the conflict between various measurements of the universe's expansion and the significant repercussions of those discrepancies will continue to drive innovation, debate, and discovery in the scientific community. What lies beyond may not only alter our understanding of the universe's past, but also its future.